Hi everyone, this is Worksheet 2.1, Derivation of the Schrodinger equation. And the purpose of this worksheet is to lay out for you some of the thought process behind where the Schrodinger equation actually comes from, and follows somewhat closely the line of reasoning that Schrodinger himself used in order to write down the equation to begin with. Okay, let's start by writing down the equation itself. Remember that the equation is negative h bar squared divided by 2m, where h bar squared is Planck's reduced constant and m is the mass of the particle we're considering. Then we've got a second derivative of the wave function, which is a function of both position and time, and it's the derivative with respect to, second derivative with respect to position, plus the potential energy function, which is just a function of position, times the wave function, equals some constant energy times the wave function again. Now this is the time independent version of the Schrodinger equation. And now we're going to write the time-dependent version of the Schrodinger equation. And the time-dependent one is the imaginary number times h bar, and then the first derivative of the wave function with respect to time equals negative h bar squared over 2m. Second derivative of the wave function again, and then the potential energy times the wave function again. This is the time dependent Schrodinger equation. Okay, now we've got to walk through some of our starting assumptions here. To begin with, I'm going to write down the expression for momentum. And the de Broglie wavelength says that the momentum is equal to h bar times k, where k is the wave number. And it equals 2 pi divided by the wavelength lambda. So that means it's going to be in units of inverse distance. That's going to be its unit. And it sort of a way to think about it is not how many cycles per distance the wave goes through, but sort of how many, I guess, radians per distance the wave goes through. All right. Then similarly, we're going to use the expression energy is equal to h bar times omega, where omega is called the angular frequency. And that equals 2 pi times nu. So this is going to be in units of inverse time, or another way to think of it is radians per time. How many radians the wave goes through for some given unit of time. Our next assumption involves splitting the energy between kinetic and potential energy. So E equals T plus V. This is going to be our total energy. This is kinetic, and T is the traditional symbol for kinetic energy in quantum mechanics, and that's because it's equivalent to temperature, so it's no accident, even though we don't really consider temperature all that much in this class. And this is the potential energy. All right, so that's our next assumption. We're also going to assume that the kinetic energy, classically, equals the momentum squared over 2m. And that the potential energy is just that function of position that we saw before. Okay, the last assumption we're going to make is that the wave function itself as a function of position and time is equal to some maximum amplitude, and then exponent I, the imaginary number, times kx minus omega time, like that. We're going to assume that that is the form that the wave function takes. And so you can imagine that we can split up this imaginary exponent into a sine and cosine. So it's just, in a sense, assuming that the wave function itself is shaped like a sine curve, like that. Okay, let's begin by converting the kinetic energy to something we can work with. This is the kinetic energy, and it equals the momentum squared over 2m. But we have up here what P equals, so that just becomes h bar squared k squared, like so, divided by 2m. Okay, so that's a good start. Let's also find the derivative of the wave function with respect to position right now. So if I get the derivative of this wave function with respect to x, and if you want to, you can pause right now and give it a try and see if you get the same answer. But I'll just tell you what the answer is right now. It becomes I k a times the exponent, and then everything inside the exponent gets left alone, kx minus omega t. And this can be written as I k psi, like that, because this function right here is the psi function. All right, now let's get the second derivative of that one. So if you want, you can pause and give it a try yourself right now. But I'll tell you the answer. The second derivative with respect to x is going to be negative k squared a times the exponent I k x minus omega t equals negative k squared psi, like that. All right, so far so good. Now let's take our expression for the kinetic and potential energy, which is equal to, right now, h bar squared k squared over 2m plus v. And let's multiply this whole expression, both sides of it, by psi. And then what we get is that E psi equals h bar squared k squared 2m psi plus v psi. But this right here is just equal to negative second derivative of psi with respect to position. So we can just rewrite this whole thing as negative h bar squared over 2m, second derivative of psi with respect to x, plus v psi. And there we have it. That's the time-independent Schrodinger equation. Okay, now let's try to get the time-dependent Schrodinger equation. And we'll start by getting the derivative of the wave function with respect to time. So if you want, you can pause and give that a try right now, but the answer becomes I omega a times the exponent I k x minus omega t. I'm missing a negative here. And we can say that this just equals negative I omega psi, the wave function. Yeah? But we also know that E is equal to h bar omega, or just dividing both sides by h bar, E over h bar. So I can say that this whole expression here just equals negative I times the energy psi over h bar. Nice. Now I can algebraically rearrange this equation, and I get that E times psi is going to be equal to negative h bar over I, the derivative of psi with respect to time. All right. Now, one critical step here is realizing that 1 over I equals negative I. And the reason for that is because if I multiply both sides times I, then these cancel out, and I'm left with negative 1, which is 1, so hopefully you see that that satisfies the equation. So yeah, again, 1 over I equals negative I. And so I can replace that here and say that this expression equals positive I h bar derivative of psi with respect to time. Okay, and I can plug this now into my time-independent Schrodinger equation, and in the end, I get I h bar time derivative of psi is equal to negative h bar squared over 2m, second derivative of psi with respect to x, plus v psi. And that's it. That's the time-dependent Schrodinger equation.